Welcome back to Smith Coding and Design. I hope everyone is having a great day. We're going to go ahead and continue along with our stainless steel widget. So with that being said, let us go ahead and jump into our Op1 toolpaths. Alright, so what I'm going to do now is I'm going to come over here to the inspection tab. So this is how we're going to do our in-process probing. So I'm going to come over here and select Probe WCS. And now what I'm going to do is select my silver CNC probe. Select OK, and then I'm going to go to geometry and select the top face of our stock, and that's going to give us a probe rectangular boss probing routine. So if we press the little arrow here for the drop down menu, you can see that is indeed what was selected. And normally I check this because the post processor right now does support probe rectangular boss, but it does not support probe rectangular boss with island. So just keep that in mind. So I am probing a rectangular boss, which is shown here. The next important step is to go to the Actions tab, select Overriding WCS, and this is where we want to enter the coordinate system for our 0 point, which here is G57, and this is why I have WCS4 written down here, so I remember for G57. In Fusion, I want to enter 4. So it's just an easy way for me to look down and remember so I don't make a mistake here. So what this is going to do is it's going to tell Fusion that we are modeling everything in this fixture relative to G57. So we can go ahead and drive our probe, avoid colliding with any of our fixturing, come down and probe our stock. And then what that's going to do is save the XY location of our stock into G54. Now it's important to note that your G54 should have the same Z location as G57, 8, and 9, right? Everything is going to be relative to the top of the rock lock base. So your Z location should not change. All we're changing is the X and Y location and saving that into G54. Z will be the same. So I'm going to go ahead and click OK. So that's how easy it is to go ahead and use in-process probing to come over here and automate probing your stock. So you can just put the stock in the vise, do everything in CAM, press cycle start, and it will handle everything for you, which is really nice. So another thing that I will show you here that I normally do, let's just go here to post process. You'll remember how I said that you want to make sure that your Z location in G54 is the same as G57 or is the same as the rest of them, which is the top of that rock lock base. So what I have here in the post processor, and we'll change this to G57, is just some custom on OpenG code. So what this is going to do is copy the coordinates of G57 into G54 when I post and when I start my program. That way it ensures that, hey, I'm just going to go ahead and assume that the stock is in the G57 position at startup, and then we'll go ahead and probe and move our XY for any variation when we put our stock in the vise. Sorry, long-winded explanation, but that's normally what I do. So let me know what you guys think of that, or what your strategy or what your flow is there. So that is it for our first probing routine. What we want to do now is we want to go ahead and jump into our 3D adaptive clearing and go ahead and rough away all of our material. So let's go ahead and do that. All right, so we are going to jump right in with a 2D face, and I'm going to select the tool, and for this I'm going to use my Haas 2-inch high feed shell mill. We'll go ahead and select that. And then before we get into the feeds and speeds, I wanted to sort of go over my findings. So this is the first time that I have used this shell mill. I just purchased the tool, and what I have been doing is on the stainless jobs I've just been facing with the 5-flute standard end mill from Haas Tooling, and it leaves a nice visually appealing surface finish. Now, so far, I am not happy with the surface finish I'm getting from the high feed shell mill. You can see here, let me see if I can get it to where it zooms in or where we focus. Now, to be fair, the finish is silky smooth to the touch, whereas the finish with the 5 flute, is more coarse. It's not as smooth as with the high feed shell mill. It's just the pattern is just not visually pleasing, at least to me, on the back side of this. So in the future, I'm going to be on the lookout for another tool or adjust my feeds and speeds, etc. See if I can get something that looks better with this shell mill, but I'll probably just find another tool. All right, so moving on to our feeds and speeds. So I'm at 1,000 RPM, 25 inches per minute. That's 5 thou per tooth. And what I'm going to do, if we go into our passes tab, we can skip the geometry tab and the heights tab. There's nothing in there that we need to change. But if we go into our passes tab, you notice my step over here is over an inch. That is way too much. I have the 5 horsepower LNC version of the style, so I'm not going to try to go over an inch in stainless steel in terms of width cut. So I am going to use 750 thousandths or 3/4 of an inch. The next thing that I'm going to do is, instead of going both ways, I'm going to go conventional, and I'll explain to you why I do that here in a minute. So again, all I'm doing here is facing off the top 20 thousandths of the material. All right, so there we go. So let's go ahead and simulate, and I will explain why I'm going conventional only. So the reason I'm going conventional and not both ways is because I have the umbrella tool changer with my style, and that means my coolant flow is coming from the right side of the spindle and sort of hitting the front face of the shell mill. And so let's go ahead and just drag the timeline here. You'll notice I go from left to right, I pick up, and I go from left to right again. And so the reason why I'm doing this is, in the past I've had issues, especially in aluminum, where I don't get a lot of coolant to the back side of the shell mill here because, again, with the umbrella tool changer and my coolant manifold, most of the coolant flow is going here to the front side. So what that has caused is, I believe, some chip evacuation issues where sometimes I recut chips and it would leave swirl marks and I wouldn't have that perfect top surface finish that I'm looking for. So when I switched to going conventional only and the coolant just hits the front side of the shell mill, I don't have to worry about that. I don't get those swirl marks and my finish looks beautiful. So that's why I'm going conventional. So I'm just going to pick up and then go into the material the same direction each time, where I have that nice coolant flow. All right, so that is it in terms of our facing operation. So what we're going to do now is go into an adaptive clearing. So I'm going to go to 3D adaptive clearing. Now what we're going to use here is one of my favorite end mills. So again, if you have ever tried to cut 316 stainless steel, you might run into the case where it sounds like a banshee screaming and you get a lot of chatter, etc. So during my learning process, I went through a lot of that, and then really I discovered this Haas, you find it here, HEPM end mill. So this is 6 flute. It's made for high efficiency machining, and it just runs beautifully, slays stainless. So that's what I'm going to be using here. The second thing that really helped improved my machining in steel was going from ER collets to nice Mari tool, hydraulic tool holders. That made a world of difference, even in aluminum. If you want to talk about a mirror finish, so if you're right on the edge of the mirror and you're using, let's say a YG1 end mill, that's what a lot of people like to use to get that mirror finish. If you go from an ER collet to a hydraulic, man, it's just beautiful. It's butter. So let's go ahead and select this end mill, and we are going to be at 8,000 RPM. So I'm going to go ahead and type that, 8,000. Sorry, it's sort of hard to see with the way that my camera is positioned. And I find that at 8,000 RPM, we are going to go 100 inches per minute, and we're going to go at a 10% diameter optimal load. So again, 8,000 RPM, 100 inches per minute with a 10,000s optimal load. Sorry, not a 10,000, with a 10% optimal load, which is 25 thou. And if you look at the recommended speeds and feeds, Haas will recommend using a 5% diameter for your width of cut or your optimal load. Now, you'll see this in Op2. If I go back here to passes, if I reduce my width of cut from 10% diameter to 5% diameter, the feed rate, sort of the sky's the limit. If you've looked at any of the shorts I've posted, I've ran this tool at 5% optimal load up to 150 plus inches per minute, and I sort of settled on 144 inches per minute with that 5% optimal load. But in terms of machining time, I find the sweet spot is 100 inches per minute, 8,000 RPM with an optimal load of 10% diameter. So the next thing that I'm going to do is I'm going to go ahead and change the stock to leave from 20 thousandths to 10 thousandths. All right, so that's fine. I'm going to enable feed optimization just so that we reduce the feed rate, when we go around any sharp corners. It will help with making sure that we don't disintegrate our end mill. All right, so that all looks good there. Let me move this up a little bit so everyone can see. The final thing I want to do here, sorry for jumping back and forth between the tabs, is I want to go 50 thou below the bottom of the part. And when we get to Op2, what we're going to do, let me grab one of the widgets again, is we're going to flip our part over, and then we're going to machine the top hat of material. And what I like to do is go a little past the bottom of the model. So after I remove that top hat of material, there is a nice faces here without any overhang or any burrs. So that way I can come in and I can probe the part geometry to go ahead and center our part perfectly in Op2. So I will be using in-process probing for that. So stick around for the Op2 section if you want to see how I do that. So that's why I'm going 50 thousandths below the part there. So to wrap things up, 8,000 RPM, 100 inches per minute, and our optimal load is going to be 10% the diameter of the tool. So I'm going to go ahead and click OK. And then what we will do is go ahead and simulate. And again, what I'm going to do here is just make sure that my tool holder is not hitting my part. Everything looks beautiful, making sure there is no collisions, etc. And so everything right now looks beautiful, no problems at all. We're just going in, removing that material. Then we're going to enter into the center hole there with that helical entry. Let's go ahead and view that, clear all the chips, and then we are going to be ready for the next toolpath. So what we're going to do next is we're going to go ahead and go into the center bore, the center hole here, and we're going to go ahead and use a pocketing toolpath to go ahead and finish that, and then we'll finish the outside of our part with a 2D contour. All right, so we're going to go ahead and end here, and then in the next video we will continue with our Op1 toolpaths. We'll get into the contours, the pocketing, the drilling, the thread milling, etc., and hopefully finish up Op1. So with that being said, I hope everyone has a great day, and I will catch you next time.